everyone! In this video, we will take a look at a real second-order system with a proportional controller in our closed-loop configuration. We'll identify the original system's parameters like we did in Chapter 1, and then we'll use that information and the equations we derived earlier in Chapter 5 to find the closed-loop poles, natural frequency, and damping ratio at various values of Kp. We will cover example 5.5 starting on page 85 of the notes. What trends do you think you will see in the closed-loop natural frequency and damping ratio? Alright, let's get started. So in example 5.5, we're going to take a look at a real second-order system in a closed-loop configuration with a proportional controller Kp. And so what we're going to do first is find our transfer function for our closed-loop system, so our GCL. And then on the next slide, we're going to take a look at how our eigenvalues, natural frequency, and damping ratio change for different values of Kp. But let's start by finding values for our GCL and some values from our original system that might help us in our calculations. So our GCL, as we've seen in the previous slides, is y over r, and as we figured out in the previous video, this equals Kp times n over d plus Kp times n. And so we know what our numerator is, it's 36, and our denominator is s squared plus 2s plus 36. And so if we plug that into our equation, we get 36 times Kp over s squared plus 2s plus 1 plus Kp times 36. If we simplify it a little bit, the other thing we can note, we can analyze our original transfer function and figure out that our natural frequency of our original system is omega n equals 6 radians per second. And where that comes from is we know that the last term of our characteristic equation is our natural frequency squared, so the square root of 36 equals 6. And then we can figure out our damping ratio, which is equal to 2 times our natural frequency times our damping ratio, which equals 2 in this case. So if we solve that, we get that our damping ratio of our original system is 1/6. And so based on what we did in the second order video, we know that our omega CL, or closed loop natural frequency, so the closed loop of our GCL, or the natural frequency of our GCL is our original omega n, which was 6 times the square root of 1 plus, and I forgot to, our original k here is 1 because we have the same 36 in the numerator, so to get k times omega n squared, and we know omega n squared equals 36, so k has to equal 1, and so our omega n CL in this case is just going to be omega n times the square root of 1 plus Kp, because our k just equals 1. And our zeta CL from the second order video is our original zeta, which is 1/6, again over the square root of 1 plus Kp, because k is just 1. And we also know from way back in chapter 1 that the equation for a closed loop underdamped eigenvalue is negative, I'm going to say zeta CL because we're going to do our closed loop eigenvalues here, times omega CL plus or minus j times omega CL times the square root of 1 minus zeta CL squared. So if we wanted to find the eigenvalues of our closed loop system, we could find omega CL and zeta CL and plug it into this, or we could find the roots of our closed loop characteristic equation, which is s squared plus 2s plus the quantity of 1 plus Kp times 36. So we have a couple different ways to calculate those values, which is what we'll do on the next slide. So on this slide, we're going to take the equations that we derived for our closed loop system on the previous slide and see what happens to those values as we change Kp. So we're going to calculate the closed loop poles or eigenvalues, closed loop natural frequency, and a closed loop damping ratio for each of the values of Kp in this table. And I'm going to kick this off by providing the original system values. So when Kp equals 0, even though it doesn't really make sense to think about Kp equals 0, when we talk about that, we're just talking about documenting the open loop system, or the original G of S eigenvalues. And so the original G of S's eigenvalues are -1 plus or minus 5.916 J. And our original natural frequency, which we talked about, was 6. And our closed loop natural frequency is 1/6 or 0.167. And so what I would recommend at this point is that you pause the video and go and try and calculate a couple of the rows of this table on your own, and see if you can come up with the closed loop eigenvalues, the closed loop natural frequency, and the closed loop damping ratio for one or two of the values of Kp using the equations on the previous slide and the value of Kp from the table. And so now, assuming you've tried to calculate a couple of these, I will fill in the table. So at Kp equals 0.5, we have -1 plus or minus J 7.28, and our natural frequency is 7.348, and our damping ratio is 0.136. And keeping going, we have -1 plus or minus J 8.426, and a natural frequency of 8.49 with a damping ratio 0.118. At 2, we are at -1 plus or minus J 10.34. Our natural frequency is 10.4, and our damping ratio is 0.096. At 5, we are at -1 plus or minus J 14.7. Our natural frequency is also 14.7, and our damping ratio is 0.068. At Kp equals 10, we're at -1 plus or minus J 19.87. Our natural frequency is 19.9, and our damping ratio is 0.05. Moving on to 100, we have -1 plus or minus J 60.29. And our natural frequency is 60.3, and our damping ratio is 0.017. And then for Kp equals 1,000, in our last row, we have -1 plus or minus J equals 189.8, and our natural frequency is also 189.8, and our damping ratio is 0.005. So looking at this table, we can notice some trends. So the first one that jumps out is exactly what we predicted when we did this symbolically. As Kp increases, our natural frequency is increasing and our damping ratio is decreasing, which is what we predicted based on the symbolic versions of these equations. And so that happened. The other thing that's interesting is if you notice, the real part of our equation stayed the same all the way through this. So we started underdamped and we stayed underdamped, and the real part never changed, which means that the relationship between zeta and omega n here stayed the same, because we know our real part from the previous slide. So S equals minus omega CL zeta CL plus or minus J omega CL square root of 1 minus zeta CL squared. And so our real part here is not changing, so that means the product of our natural frequency and our damping ratio is not changing. We also know that if we take the absolute value of our eigenvalue, it equals our natural frequency, which is why when our real part starts to get pretty big, our natural frequency ends up being the real part, because not only is our zeta squared term pretty small, taking the magnitude of 1 squared plus 189 squared and taking the square root, you're going to basically get the same number there. And so this shows us the trends that we predicted symbolically, but as with a lot of calculations like this was fairly tedious to do by hand, and we only did 8 values of KP, and so it might be nice to graphically visualize what's going to happen with KP. So on the next slide, we're going to actually plot out our eigenvalues as they change with KP. So here in figure 5.4, we have a complex plane, and we're going to plot those eigenvalues that we calculated by hand in the previous slide. And so I'm going to put a mark at -1 because our real part was always -1. And we started at 5.916 for the imaginary part, and make this symmetrical, and we start at -5.916 for a complex conjugate. So I'm going to put an X there at our original poles, and I'm just going to draw an arrow that goes straight down and straight up that represents what we calculated, because we saw when we cut the trend when we calculated is the real part stayed at -1, and then the imaginary part just got more and more imaginary, or bigger and bigger, as k increased. And so essentially what it is doing is it's getting more and more underdamped. And so we can actually visualize then how our eigenvalues are going to change as KP changes. And so this one, we calculated some values, and it was fairly easy to understand what was going to happen to draw it by hand. But as with anything that we draw by hand that turns into a useful plot, there's a MATLAB command for that, and we'll take a look at that on the next plot. So here in MATLAB example 5.1, we have what we call a root locus plot, and we use the rlocus command to generate it in MATLAB. And what this does is it plots exactly what we just talked about in the previous plot that we drew by hand, and it's going to show you where the eigenvalues are going to move as KP changes. So we can see on our plot we have x's, which is how we drew our plot. And if you look, this tick mark corresponds to 6, and this tick mark corresponds to 6, and our x is just inside of that. And if you had enough tick marks, you could, and you look at this, you could probably convince yourself that this is at -1. And so our x's are exactly where we started, and then they go off and get more imaginary along that -1 line. But, and so this is, if you look here at your x and y axis, you have your real and your imaginary axis, just like we would expect from our complex plane. And if we look at the markings on the outside, the 0, the -5, the -10, the -15, and then our even markings here, the 0, the -2, -4, -6, -8. So the markings on the left and the bottom are the markings of our complex plane, like we've been plotting eigenvalues all term. But now our grid looks a little different. We have these circular arcs, and we have these straight lines that are coming out from the origin. And those represent some very specific and useful terms for our system design. And so the arcs, or the circular arcs, are constant values of natural frequency. So I just highlighted the innermost arc, and that so if an eigenvalue lands on that arc, it has a natural frequency of 2, that first number. The second arc has a natural frequency of 4, and then the arc that comes close to our eigenvalue is at 6, which our x ends up right on that 6 because our original system had a natural frequency of 6. And so if you end up anywhere on that arc, you have a natural frequency of 6. If you remember from our original analysis, we also said we had a damping ratio of 1/6. And so the what I sometimes refer to as sunbeams, or the lines that radiate out, which is why I call them sunbeams, radiate out from the origin, those are lines of constant damping. And so this particular line, wow, that's really dark. So this particular line that goes up is 0.86. And so that means that anywhere along this line, you have a damping ratio of 0.86. And if we remember from our original system, our damping ratio was 1/6 or 0.167, and it looks like our x's are right on that 0.16 line, or really close to it. And so the cool thing here is if you know what combination of natural frequency and damping ratio you want your system to be at, you can look, and if it intersects one of these lines of where your eigenvalues can go, it is possible to find a KP that will equal that particular value. And so these root locus plots end up being really useful in giving us an idea of what natural frequencies and damping ratios we can achieve with a proportional controller given our original system. And so the way we enter this into MATLAB, we look at our code sample over here on the left, is we put in our transfer function just the way we've been entering transfer functions for Bode plots and everything else in this term. You have a transfer function with 36 in our numerator and s squared plus 2s plus 36, or coefficients in the denominator. And then we use the rlocus command, which stands for root locus, which is the official name for this plot. And so this is just a brief introduction into the benefits and what the root locus tells you and how to generate one in MATLAB. And in next week's videos, we will dive deeper into the theory and the math behind our root locus plots and how we're going to use them in detail in this class. And so in this example, we calculated the closed loop pulse, closed loop natural frequency, and closed loop damping ratio of our transfer function of 36 over s squared plus 2s plus 36. Then we plotted those eigenvalues and then looked at our root locus plot, which is a very specific and useful plot of those eigenvalues, which shows us our possible closed loop eigenvalues as Kp changes from 0 to infinity, which will allow us some very helpful insight into our controller designs for proportional controllers going forward. Thanks for watching.